Okay, let's unpack this. Imagine you've got one of these super powerful large language models, right?
Yeah,
And you want to make it even better, sharper, maybe more consistent.
the usual goal.
Exactly. Now, what if I told you you could do that not with weeks of complex trooping, not with mountains of data, but with just one piece of data
Uh-huh.
and maybe like 10 minutes of compute time?
Okay, that sounds, well, almost too good to be true.
Right, seriously. But that's the kind of potential breakthroughs we're digging into today.
Hmm.
Our topic is one-shot entropy minimization, EM for short. We've got a bunch of source material, research papers, notes, FAQs, study guides, all about this seemingly magic technique.
That's right. And our mission here is really to get under the hood. What is EM? How does it pull off this, extreme efficiency? And crucially, why do the researchers think it's such a big deal academically?
Yeah, what's the clever bit? How does it stack up against the standard ways, like reinforcement learning? We're really focusing on the innovative thinking behind it.
Because that core idea getting similar or even better results than those huge expensive methods, but with tiny resources that's potentially revolutionary.
Absolutely. So let's start right there. What exactly is this entropy minimization?
Okay, so the sources define it as a new unsupervised post-training method designed specifically for LLMs.
Unsupervised, that jumps out immediately. No need for human labels saying this is right, this is wrong.
Exactly, no costly labeled data. And the basic idea, well, it's about getting the model to be less uncertain about its own output while it's generating text.
Less uncertain.
Yeah, it tries to minimize something called token level entropy. Think of entropy as like a measure of the model's confusion at each step.
Okay, so if it's unsure about the next word, it gives lots of words a similar low chance, high entropy.
Precisely. High entropy means the probability is spread out. Minimizing entropy forces the model to put much higher probability on just a few likely options to become more certain.
And the paper says this whole thing is built on just two really simple assumptions. That sounds elegant.
It is quite. First, that LLM generation is naturally a bit random, stochastic. It can often produce different plausible outputs.
Makes sense.
And the second assumption is key. The idea is that the correct answers, or the sound lines of reasoning, tend to be the paths where the model is already more confident. They generally have lower entropy than the incorrect paths, the ones that kind of wander off. So if you push the model to be more certain overall,
You're kind of implicitly steering it towards the better paths it already vaguely knows.
that's the core intuition, yeah. By minimizing uncertainty, you amplify the signals for good reasoning that are already there.
And technically, you said unsupervised, no labels, no complex reward design like you get with RLHF.
Right. None of that. It directly minimizes the conditional entropy at each step.
Conditional entropy being the uncertainty about the very next word, given what it said so far.
Exactly. And from a technical standpoint, the math works out nicely. The loss function they minimize is differentiable. It has a closed form objective. That makes the optimization much simpler compared to, say, the complex setups you often need for RL. That simplicity is part of the secret to its speed.
Okay, speed. Let's get to the really wild part, this one-shot efficiency.
Yeah, this is where you see the academic claim really hit home in practice. The research shows performance boosts on reasoning tasks
Uh-huh.
that are as good as or sometimes better than methods that need thousands of data points and tons of training time.
And EM does this with?
One single unlabeled data point and about 10 training steps.
Wait, 10 steps, one data point. That's astonishing compared to the usual thousands for RL.
Exactly. The sources really hammer this contrast. Thousands versus one, thousands of steps versus 10. The resource saving is just immense.
That's not just tweaking, that's a different category of efficiency.
It really is. It makes this kind of powerful post-training potentially accessible to way more people, labs without massive GPU clusters.
Okay, but how? How on earth does it manage that? Such rapid results from so little input. The paper must explain the mechanism, right? They talk about Lobit's shift.
They do, and this is central to their explanation. So lobits, think of them as the raw scores the model gives to every possible next word before it turns them into probabilities.
Got it. The pre-probability scores.
Right. And logit shift is about how the whole distribution of these scores changes after EM training.
And the key finding, EM causes
A rightward logit shift.
meaning. What does that look like?
Imagine plotting all those scores. A rightward shift means the entire curve moves towards higher values. The model gets more confident overall.
Okay.
But critically, it's not just a uniform boost. It seems to disproportionately push up the scores of tokens that were already reasonably high. So it concentrates the probability onto a smaller set of likely candidates.
Ah, it narrows the focus onto the high probability options.
Exactly. The authors argue this widening of the high probability path makes it easier for the model to follow consistent, correct reasoning. And understanding this mechanism, how it reshapes the scoring, that's a key academic contribution here.
And they found this is the opposite of what happens with standard RL.
That's what they observed, yeah. RL training, they found, tends to cause a leftward logic shift.
Leftward, so scores go down.
Overall, yes. Their hypothesis is that RL, using external rewards, works by punishing high probability tokens that turn out to be wrong. It suppresses those scores.
So it pulls the distribution left.
Right, so both methods change probabilities, but through these opposing global shifts in the underlying logics. And the researchers argue EM's rightward shift is better for maintaining general reasoning coherence.
Interesting. So this whole Lobitz shift idea leads them to a bigger conclusion about what EM is actually doing, doesn't it?
It does. They argue EM isn't really learning new facts in the traditional sense. It's better thought of as a distribution shaping tool.
Shaping, not teaching.
Exactly. It takes the knowledge the model already has somewhere inside, and it just reshapes the probabilities to make the model more confident and consistent in using that knowledge.
And the evidence for this shaping idea comes from something quite odd, right? The way loss and performance behave.
Yes, this is fascinating. They found this decoupling between the training loss and the actual task performance.
How so?
Well, you look at their graphs, like figure 2 in the paper, the EM loss function, the thing is trying to minimize drops super fast. It basically flatlines around step 10.
Okay, that sounds good.
And right at that same point, step 10, the model's performance on the reasoning tasks hits its peak.
Ah, loss down, performance up. Makes sense.
But here's the weird part. If you let it keep training past step 10, the loss continues to go down slightly. The model gets even better at minimizing entropy. But the task performance starts to drop.
It gets worse, even though the loss is improving.
Yeah, they call it overconfidence. Pushing entropy down too far makes the model too rigid, maybe amplifying biases, and it starts performing worse. It gets too certain.
Wow, so that rapid peak and then decline is strong evidence that the useful shaping effect happens incredibly quickly.
Precisely. Around step 10, the beneficial distribution shaping is done. More training just pushes it too far, which explains the whole 10 steps thing.
Okay, so if the shaping is that fast, the single data point you use must be pretty important. You can't just pick any random one.
Absolutely critical. The sources stress this. You need an informative prompt. And they came up with a neat way to pick it. A variance-based selection strategy.
Variance-based, how does that work?
They look for prompts where the model's performance is really inconsistent. Specifically, they measure the variance in its pass at K accuracy.
Right, pass at K. You run the model K times on the same prompt and see if any of the answers are right.
Exactly. So high variance in pass at K means sometimes the model gets it right, sometimes it gets it wrong, sometimes maybe it gets close. Its behavior is all over the place for that prompt.
Ah, so the model is fundamentally uncertain about that specific problem. It's, like they say, straddling the decision boundary.
Perfectly put. It's not trivially easy, but it's not impossible either. These are the prompts where the model is most confused, where the entropy is highest, and where minimizing that entropy gives the biggest signal to nudge it towards consistency.
That makes a lot of sense. Training it where it's most wobbly to make it stable. They mentioned an example, right? Some math problem.
Yeah, a pressure cell physics problem from the Numina math dataset, selected because the base models showed high variance on it.
Cool. Okay, what about other factors like temperature, the randomness knob during generation? Does that interact with EM?
It does, and in really interesting ways. Two different roles here. During the EM training itself, they generally found higher temperatures during training led to better average performance after training. Although moderate temperatures like 0.5 sometimes hit higher peak scores, but with more randomness between runs.
So a bit of randomness during training helps.
It seems so on average, but then during evaluation when you're actually using the EM trained model.
Is it the same? Higher temp is better?
No, this is another key difference they found compared to RL. For EM trained models, performance consistently goes down as you increase the evaluation temperature.
Really? So you want zero temperature, greedy decoding.
Pretty much. The best results come from just taking the single most probable token at each step, temperature 0. This is often the opposite for RL models, where sometimes a bit of temperature helps find better answers.
Why the difference? Does it go back to the logic?
Exactly what they propose. EM's rightward shift concentrates so much probability on the top token that it becomes very reliable. Greedy works great.
Whereas RL's leftward shift might mean the best token isn't always ranked number 1, so you need some temperature to find it.
That's the hypothesis. It highlights a fundamental difference in how they sculpt the probability landscape. This temperature sensitivity is another distinct signature of EM.
Okay, fascinating. What if you try to use both EM and RL, like chain them together? Does the order matter?
Oh, it matters a lot. They found a really clear asymmetry here.
Okay, what if you train with RL first, then apply EM on top?
Performance went down, steadily declined in their tests.
Any idea why?
They suggest maybe EM applied after RL messes things up further, perhaps amplifying distortions RL already introduced, or clashing with the RL objective somehow, that alignment tax idea again.
Okay, so EM after RL is bad. What about the other way around? RL after EM?
Now that worked. They saw consistent performance gains doing it in that order.
Interesting. So EM first seems to prepare the ground for RL.
That's the suggestion. EM might enhance the base reasoning or reshape the distribution in a way that makes the subsequent RL tuning more effective. It gives RL a better starting point, perhaps.
That's a really practical insight about combining these. Sequence is key. So how widely does EM work? Is it just for math or specific models?
They showed it working consistently on math reasoning benchmarks across several different base models. They mentioned testing LMA-3.1-8B, various QN 2.5 models, 7B, Instruct 7B math. So decent versatility there.
But are there limits? Does it always give a huge boost?
There seem to be limits. The size of the improvement seems tied to how good the base model was to begin with. You can't polish it. Well, you get the idea. You're boosting existing capability, not creating it from scratch.
Right. Any cases where it didn't work well?
Yeah, one interesting exception they noted, they tried applying EM to a model that had already been really heavily tuned using RL, something called simple RL Zhou.
Yeah.
Performance dropped, similar to the EM after RL ordering result.
So again, maybe it clashes with heavy RL tuning. It's best for models that haven't been intensely optimized that way yet.
That seems to be the pattern emerging from their results, yeah. They even suggest it could be useful as a sort of confidence compression step applied to models that have had supervised fine-tuning, SFT, or maybe just lighter RL.
Okay, this has been a really interesting look at a potentially powerful new tool. If we had to sum up the truly innovative parts of one-shot EM,
I'd say the big headlines are, 1, it's fully unsupervised. 2, the extreme efficiency, that one-shot 10-step thing is just remarkable. 3, the mechanism insight identifying that rightward logic shift and framing EM as distribution shaping. And 4, the practical result, getting RL level gains with a tiny fraction of the resources.
yeah, it feels like a different philosophy, not teaching the model new stuff, but helping it become more certain and consistent about what it kind of already knows. Reshaping confidence, not adding knowledge.
Exactly. It's about unlocking latent potential efficiently.
And the researchers have ideas for where to go next, right? Stabilizing it, trying other tasks.
Yeah, they mentioned stabilizing training since it can be a bit random, exploring things like dialogue, summarization, maybe code generation. Also looking into confidence calibration, does it become overconfident? And systematically figuring out the best ways to combine it with SFT or RLHF.
Okay, so here's the final thought for you, the listener, to chew on based on all this. If EM works so well, boosting reasoning just by making the model more confident in paths it already leans towards, and it does this with almost no data or training. Does that suggest that maybe these base LLMs already know a lot more, have a lot more correct information latently stored than we typically get out of them? And maybe the big challenge isn't always teaching them more facts, but finding better ways, like EM, to help them confidently and consistently access the right stuff they already have inside.